actually somewhat completed the homework. For the first time in like 2 weeks.
Really?
Yeah, I just haven't.
I just write down something.
Yeah.
You know,
Yeah, no, I'm really stubborn when like it's not, I don't know. I should.
it's hard, especially if you know you're not certain to 100%
Yeah, no,
degree.
yeah, no, I'm just looking at it, I'm just like, this is so like, yeah.
And then yeah, she's grading it pretty accurately. She's giving us pretty hardcore feedback.
Yeah,
There's,
I wouldn't know.
you want to make sure that some of your arguments are logical before you submit them. I know what you mean.
Yeah, I mean, you know, it's somewhat logical, but the answers are, look, yeah.
You saw that steak on you.
Yeah. They got downgraded.
Oh, that's an upgrade, my friend.
It's
Got a
like,
stapler, bro?
yeah. Share the steaks. I don't know. That's the one.
Thank you.
Oh, sorry.
Thank you.
You're welcome.
I forgot my actual like engineering paper, so I turned it in this on my Dungeons and Dragons paper.
Yeah.
And she notices and is like, so I'd be like, oh my gosh, really? No way.
Finally know my study techniques.
All right. Oh, this is the one. Note. What did I do wrong? Nice. What's your last name? Oh,
Roads.
Rhodes? Cool.
Mother's maiden name?
Oh yeah.
That's a mother's maiden name?
Mother's maiden name?
Because
Because they're Aussie.
Color of your first car.
Yeah. Naming your girlfriend.
Childhood best friend in the second grade. I don't know.
Alphonse.
Is it actually? Nice.
Poor kid. Kids can be brutal about names. Even my name was brutalized.
Oh man.
I don't think nobody could pronounce my name, so they couldn't brutalize it.
I was called Tildo for a few years. Still called now lovingly by my friends, but
Oh man, people love the last name Hannah. Hannah Montana. Wah.
yeah.
Oh. Little bastards.
Kids suck. That's why. I'm no offense.
I don't know. Adults kind of suck too sometimes.
Yeah, but I can choose to avoid people. If I have a child and I'm like, oh damn, I don't like you. I'm not like, I'm stuck. You know. Of course, it'd be my fault that I don't like them.
Yeah, true. It's kind of similar to marriage, though. I mean, I guess it's pretty
I
popular.
think you have plenty of choices.
Yeah.
In that matter.
Hello.
Hello.
Oh, pretty cold too.
Yeah. Brutal upstairs, especially.
Yeah, it is.
Yeah, it was on the third floor earlier. It was pretty bad.
I'm like this close. Like I've got like a perfect blanket for that's like the size to be able to like just politely put on myself, and I've been this close to bringing it like 3 or 4 times of just like, all right, I'm home. But I've never done it. Not
You
done
could
it.
make like a tent.
Just bring up space here.
Yeah.
I was just about to say that. Just put one.
If I could plug in my laptop and run through my GPU code, you have it. Just go ahead. Poof.
Oh, heat HUD. I mean, it could be a physics project.
Yeah.
Have you ever heard my laptop go into overdrive? I've got a button for it.
Why do you have a button for it?
Do I?
Why do you have a button for it?
If I know it's about to like, if I know it's going to need it, I can just like preemptively just for it instead of having it get too hot and then like do the thing where it's trying to cool down, but it had to slow down during that time. I'm just like, do all you got.
Nice.
How much for?
Five.
She back for how much for or no? Because I didn't find any
I don't know, I didn't turn it in, so.
I don't-
mailbox or no.
I've got my back.
You want a stapler?
I'm loving all this happy talk
Hello.
between all of us as if just to compare it next week. How scared to death we're all going to be instead of us all happily talking about anything. We're all going to be like, be strong.
I don't know, there's no point in talking about it.
It's not here.
There it is. Just gripe. Gripe and moan.
I gave yours, right, already?
Yes, I have mine.
This is yours. Pretty cold in this building. Huh? Pretty cold.
It's freezing.
They're not even down the heating, it looks like. They're supposed, they said that they'll turn it on October 10th, but apparently it looks like they go building by building, it's not flipping by a switch, so. I think this year early I called, right? Maybe this, yeah, I mean, because my friend in Indianapolis, she told me today, Fatima, today it's their snow in Indianapolis.
How far up in Indiana?
Indianapolis, I didn't know. No more. Yeah, it's just cold front.
Oh, that's easy.
Alright, should we get started?
Board's dirty. Board's dirty.
Dirtier now? Dirtier than before?
No, it's
It's just dirty.
Huh?
It's just dirty overall.
It's just dirty.
Because of that, I think the marker pens have to be, if you don't use the right marker pens, you know, it leaves the residue. And then I take it off.
Yeah.
RPGs.
Yeah, I know, but still. This is pretty good.
It's better than the still cleaner in the TA office.
All right, what I want to do today is study the heat diffusion equation in the cylindrical geometry. Consider the steady state temperature distribution. We started with that when we did PDE, right, originally, but we didn't have a specific problem. So, so we'll just get started with that and maybe get started with Fourier series also today, we'll see. So, so we again have a, let's say, so it's an infinite right? So it's a infinite, semi-infinite cylinder of radius A. So we normally, position vector is written in terms of rho phi. This is a position vector. We project that in the xy plane, that's your rho. Phi is the azimuthal angle, and z is the position along the z-axis, right? So rho phi z are the independent coordinates that we normally use for anything with the cylindrical geometry. So what you're given is the base of the cylinder is held at temperature T equal to 0, and the curved surfaces they are held at 0 degrees Kelvin, and the temperature at z equal to infinity goes to 0. Okay, so if U represents the temperature, this variable represents the temperature. What we have is the following boundary condition: U at z equal to rho phi z, right? Rho phi z equal to infinity, it goes to 0. The temperature at z equal to 0 is held at, that's what we have. And then U at, since the radius of the cylinder is A, we have A phi z. Okay, so at the surface of the temperature is 0. Okay, so the surface of the cylinder. And we'll also assume that the temperature is actually symmetric. Okay, the temperature distribution is actually symmetric. Okay, so we're going to be solving the heat diffusion equation subject to these boundary conditions. So we know that this is the diffusion equation. So steady state temperature distribution means this is equal to 0. So we are solving the Laplacian equation basically. So what is del square for the cylindrical geometry? Up to this point, everything is the same, right? I mean, you know this. How do you write del square in for this geometry?
D squared over D squared rho plus D squared over D squared 5 plus D squared over D squared Z.
No.
No.
That is fine if it was, they were Cartesian coordinate. Remember, it's Cartesian coordinate with, partial of u with respect to x, partial, that. But in cylindrical coordinate, that's what we had to go back, how to represent del square in curvilinear coordinates, right? I mean, that's what we started the course with, right? So del square u, the formula is given, whether it's spherical or cylindrical coordinates, it's given by the following formula. So you have to apply that. I'm calling this u as temperature and u1 is our independent variable. So u1 is rho, u2 is phi, u3 is z. Partial u with respect to u1 plus partial with respect to u2 of h1, h3, h2. I'm going to write this generally and then we'll come back and substitute. Okay. Just because our scale factor in Cartesian coordinates h1, h2, h3 was 1, okay, so we could get, whatever you said was okay then. But now, what is h1? We derived these scale factors. Do you remember? H1 is 1, H2 is rho, H3 is 1, right? So this is what we had done. So we had to substitute all that into this, and that is your expression for del square u in cylindrical coordinates. Okay, and in spherical coordinates, accordingly, these things will change. H1 will be r, H2 will be r sine theta, and H3 is 1 over here. So all these things we proved also previously. Okay. So that's a major difference. Okay. So del square u in cylindrical coordinates is nothing but 1 over rho, partial with respect to rho, because u1, let me write down here, u1 is rho, u2 is phi, u3 is z, okay? The position along the z-axis. H2 is rho, and these are 1, so I can write it as partial u with respect to rho, that will be your first term. Partial with respect to phi is my second independent coordinate. H1, H2 over, H2 is now in the denominator, so it's 1 over rho, partial of u with respect to u2.
U2 is 5.
Sorry, phi, of course. With respect to phi, plus partial with respect to z. H2 is in the numerator, that's the one which is rho, partial u with respect to z is equal to 0. So all I've done is use the correct expression for del square in cylindrical coordinates. That's all I've done. So it's not as simple as we had it in Cartesian coordinates. Okay, so it is more complicated expression. All right, I have it right. rho is in the numerator. Okay, there's the denominator, there is the numerator. Okay, all right. These conditions here so they have space. Basically, we are solving del square u rho of 5 is equal to 0, subject to this boundary condition. All right. Let me take rho inside because I don't want to forget that. So let me first 1 over rho. This is 1 over rho, and this is independent of that. So I can put 1 over rho squared outside. And the last one, I guess I can cancel it. Okay. I guess this is the last one, I think. All right. So what's the next step in partial differential equation? 1 over h1, h2, h3, right? Which was there. I just pulled it in. Okay. And that is of course d square u over dc square and d square u over d phi square. Okay. It is this term which is got changed. Okay. I mean, when you said that, it is the first term which is complicated. Others are, similar to what we have because h2, h3 there. Because of the way the scale factor worked out. Okay. All right. So what is the next step? This is PDE. What do we do next? Separation of variables to convert that into ordinary differential equation. Right. So what we do is u rho phi z. We write it as product of 3 functions. The capital letters of the function and small rho phi and z are the independent variables. Okay. So when you do that, so del square u now becomes what? So I can pull phi and z out because it doesn't depend on rho. So I can write this as phi z over rho. And then what? It becomes ordinary differential equation. So I can write it as d to the derivative of this rho. Now I can write it as dp over d. That's it. That's the reason for separation of variables method. This has become normal derivative, not partial derivative. Plus, this is what? P times z over rho squared. Plus, what's that term? P phi d squared z over dz squared equal to 0. Okay. So now this is ordinary. So del square u has become that. So we converted this into ordinary differential equation, right? Everything is total derivative, so that's become ordinary differential equation. Alright, so what's the next step? You convert PD into ODE now.
By rho phi z.
P phi z, so that I have terms which are functional rho d phi only, those are fixed, okay? So divide by P phi z, these functions. So if I did that, I'll have 1 over the function P, 1 over rho, right? And then I have 1 over rho squared, 1 over phi, d square phi, d phi squared. So this is a function, and I have 1 over z, d squared z over dz squared equal to 0. Right? Once you do that, what we see is the last term is a function of z only, right? Others are a little bit mixed. You got rho and phi. It's got function p is sitting there down. So yeah, so this one at least we can take it to the right hand side, right? So so if I took this to the right hand side, what we can say is this is a function of rho and phi, and this is a function of z only, and that's not possible unless this term is a constant, right? I just took this to the other side. So what can we say about this function? So we know it's a constant. Should I put plus minus k squared? Which sign should I choose? These are your separation constants. So I need to get the functional form and all that stuff right now. Not only functional form, coefficients and all that form. Each of the functional form of all these things I need to extract. So what do we know about the function? What we know that u at z equal to infinity has to be 0. Okay? So that means z at z equal to infinity has to be 0. Right? Because of that boundary condition. The first boundary condition. So this implies z at z equal to infinity has to tend to become, that must become 0, right? So which sign should I take? If I took negative sign, what do I get?
An oscillator.
Oscillator. Can we do that? No. The only way is if I take the positive sign, then the solution is combination of exponent kz and minus kz. So I can write the solution as anything like this. There's nothing but exponential of plus kz plus exponential of negatives. Actually, let me put a small z because we also use the function.
Since it has to decay.
And then it as dk, so we cannot have a equal to 0. So only we know that this has to be at this form at least. So this is b times minus a z, something, or some constant. So we have roughly something. Okay, we have written in everything. We have to find what is k, b, and everything. Right? Okay, so the first term is at least. So now that we know that this is nothing but minus, this was positive, so this is negative, so we can just take it to the other side, right? I mean, so now I'm going to bring it to this other side. this is plus k square equal to 0. So, okay, that was negative, and then bring it back again. So I have 1 over z d squared, when we, so that is plus k squared. So what is the next term that we can eliminate? What do we have to do now? This term looks nice, simple, but I have this guy sitting there. Right? So can we multiply by rho squared? So that I have a term which is a function of phi only, and we can take it to the other side. Alright, so multiply this particular equation by rho squared. I'm just going to call it some equation 2. Okay. If I did that, I have rho then I have a term only dependent on phi. Plus k square rho square equal to 0. Okay, now this term, now I can pull it to the right hand side and use the same argument. A function of rho cannot be equal to function of phi unless it's a constant. So, so let's pull that out. And then cancel it. Alright. Alright, so this also has to be a constant, under separation constant. Each one of, no, this is a function of rho only, this is a function of phi only. So I can say this guy also has to be a constant. So, or I can, let me just, I put this negative sign a little later. What about, what should this function phi of phi be? Should I choose positive or negative sign based on the boundary condition and everything? Negative? If I choose a negative sign, I can get a general functional form a sine m phi. I'm going to call it under constant a c sine plus d cosine of m phi. So what can I say about this?
preconditions in phi?
I have said something, there's one critical word here. That says something in the azimuthal plane, you know, the temperature has, it is independent of phi. Okay. Okay, so we have like, right now, let's keep it like that, let's proceed, okay? At least we know it's a combination of sine and cosine, okay? Let me proceed a little bit more and then, so this is what, plus m squared, right? Because that's negative m squared. So plus m squared, so I have a minus m squared here, equal to 0. Okay, so I have a equation in rho also, but this function p is sitting down, so I have to multiply by that, okay? So put that also upstairs, okay? So this one, multiply by p, and so what is that equation? So this is some combination, it looks like a sine n phi and cosine phi, okay? This we know should be decaying, okay? And what is p? Do you recognize the differential equation?
The Bessel?
Yeah. Bessel was what? X squared d squared y over dx squared x dy d over dx x squared minus n squared y equal to 0. Then Bessel function was jn x. So here what is how will you write the Bessel function? The solution here. So p of rho. How will I? Yeah, we have identified Bessel function. But what's the subscript and what is its argument? Then the solution was j sub nx, one of the case. One solution was y of x, one of the solution was that, right? J sub nx. So that is what? Jn, right? And what is the argument? X looks like k rho. Alright? So that's a solution of that, but that's only one solution, okay? This is also linear combination of just a sine and cosine, two solutions, right? I mean, second order differential equation, it'll have two, right? The other one is the Neumann function, which is normally for rho equal to 0, it blows up, and you all set the constant equal to 0. Okay, so this is not considered, we only consider the Bessel function, okay? So that's the, so this is nothing but some constant, I'm just calling E at this point, Jm k rho. Okay, k is one of the separation constants that we got. Okay, so we have to determine all these things, right? And this one right now seems like sine of n phi plus d cosine of n phi, right? This is phi. Now, as I said, we have this condition, which is the solution temperature distribution is actually symmetric, okay? So what it really means is m has to be exactly equal to 0, then only you can remove the phi dependence, okay? So the solution here, the m, it also now tells you what is the value of m here. it's not, so m has to be, I don't even have to worry about sine or cosine, but m is exactly equal to 0, so only the cosine, other one will survive. It's a constant, right? So m equal to 0, so the solution is like this, okay, j is 0. So this is some constant d, okay, so I'm going to combine e, b, d into another constant, okay, let's call it a at this point. All right. So we know what this has to be. It has to be Bessel function of the 0th order, not any Bessel function, only at the 0th order. And this is really just 1, okay? And this is exponential of minus kz, okay? All right, now, so we applied this already. What about this? We applied this, that's why we got the exponential of minus kz. This will apply last. What about this? Rho equal to a, phi, any phi z, only on the surface of the cylinder, it is 0. So what does that tell you? This particular boundary condition. Applying this boundary condition u a phi z equal to 0, what does that tell you?
Oh, you can use it to find k.
K is something we have to determine, okay? K, this, it'll come, okay, about this right now. K is a separation constant that we don't know what it is, right? Yet, yeah. But, so this condition when you apply, what does it tell you? Because this is your solution, temperature, right? This is solution. So A times, where do you substitute? You say J is 0, Ka equal to 0, right? So it tells, this tells you, because rho appears only here, right? So that's what, that has to be 0. So what is your Bessel function? Do you remember your Bessel function, how it was given? N factorial n going from 0 to infinity. Okay, this we prove for the solution using the power series method. Here, if nu is equal to 0, what happens to that? We need J naught x. Gamma of n plus 1 times n factorial. So what is gamma of n plus 1?
In gamma n.
That's also true, but it's also n factorial. Remember, if it's integer, that is a recursion relation, yes. But it is, when you do that, it actually gamma of n plus 1 becomes n factorial. Right, 1 less, right, then 1. That's what we proved, right, using that recursion relationship, you get that. So this is nothing but n factorial. All right, and then we had expanded this, and we know that, term by term when you expand, this was nothing but 1 minus x squared over 2 squared. And the next term was x power 4. 2 squared, 2 power 4, blah, blah, blah. Okay. I had said this J naught x looks like cosine function. It's not quite cosine. This is nothing but I just have expanded this summation, okay, 10 by 10. So this is for n equal to 1, okay, that's what happens, you can make a sign and then, you know, I've written it like that, but, okay, it's coming from there, actually. All right, so we know what J naught x looks like, and what we're saying is, our condition is J naught x, this is equal to 0, right? That will tell me something about x. So we have to find, we can plot J naught x as a function of x. It's an oscillating function. Bessel function is nothing but an oscillating function. Okay. So we need to find the roots of, you know, where exactly it becomes 0, J naught x. So this becomes, this can be done numerically actually. I mean, you'll just do it and it becomes 0 at 2.4, this is at 5.5, and the third node is something 8.3 or something like that. The next one is 8.65. That's not important, but what you have to understand is, what does it tell you about x? I mean, this solution. So this becomes 0 at certain points, right? That is, Ka is 0, or K1A is equal to 0 when this is equal to, the first 0 is at 2.4, right? Okay, the second one becomes 0 in K2A, on this second node, is at 3.5 or whatever that, 5.5. So what it tells you is, this K that we had in the separation constant, it is not a continuous variable. It is a discrete variable. K is nothing, it is very fixed value. It can be 2.4 divided by A, or 5.5 over A. So it's a discrete variable. So I have some more information about K. I have to put a subscript, K is Kn, and then we have to, this superposition principle of the solution will happen, okay? So K is discrete, okay? It is not, it's quantized if you want to say in, quantum mechanics, that's what I mean. So it does not take continuous value. It's not like 1, 2, 3, 1, 1.1, it's not that. It has got very fixed value, because it's this J0x equal to 0 only at certain values of x. Okay, this first one I'm calling it x1, x2, these are like almost modes or something, okay, x3, x4, wherever it becomes 0. So that tells me that this variable is discrete. K is not continuous, but it is discrete and it's got very specific values. So K, the separation constant, is discrete. Okay, with K1 equal to whatever the first node is divided by A. K2 is the next node divided by A is of course the radius of your cylinder. Alright. So what it tells me is then this solution that I've written down here so U rho phi Z can be written as J0, some constant A, I'm going to put now, Kn rho exponential of minus Kn Z, and going from 1 to infinity, okay? So this K, the solution, because here it is not just one value of K, it has several values, right? But they're also discrete. So I need to, the complete solution is superposition of all different values of K it can take. Okay, so that's a superposition principle that we normally use. All right. So now we have this, now we have to determine all these things, right? I mean, I have to determine all these things now further. So what else can we use? We have used all these things. We have used this boundary condition. I can use this one now, right? z equal to 0, I have this, u rho phi, it tells me it should be something like this. Alright, and going from 1 to infinity. So we have to find this coefficient too, right? I mean, this is the solving this completely. Previously, we just left everything like that. In Cartesian coordinate, it was easy. We could use Fourier series to get this last coefficient, right? And now we have to exploit all the properties of Bessel function to extract this last, coefficient. So what can we do?
So equal, all that equal to T naught?
Yeah, this we put T naught, okay? Yeah. I need to extract out this guy, right? I mean, I need to find out something, and this is what I have to do. Once I find a sub n, I come back and put it here. That will be a complete solution. So the last part is always difficult. Getting that coefficient requires the knowledge of everything, right? The normalization property, Bessel function, orthonormal property, and all the property Bessel function that, that's why we had to learn all those things, okay? So I'm going to let's just write down here. All right. So orthonormalization, I think with both of them, but okay, let me just write down first. So Bessel function, is it in Sturm Liouville form? X squared d squared over dyx plus x dy dx. Is it in plus x squared minus n squared y? Is it Sturm Liouville form?
Not quite.
Right? It's not. Right? So we have to do the integrating factor and all that. The integrating factor is x, just as you have here. So what we have is x times, I'm just going to write down this expression, j nu alpha x, k rho and all that, right? And j beta x. Okay. Of course, it's 0 if alpha is not equal to beta. Otherwise, it is the following. I'm going to remove that because I need only that from now onwards. Alright, so this is 0, of course, if alpha is not equal to beta. That's what we had learned. Yeah.
So if alpha's not equal to beta, but what about mu and beta?
So not nu, sorry, this is nu, sorry. I'm keeping the same nu. All right, and 0 to a, j square u, nu alpha x dx. Okay, so that's a normalization. That's orthonormal property. This is a normalization property. Okay, that is given as a squared over 2 j squared u plus 1 x. So this is one of the reasons when you have, whether it's Legendre or associate Legendre polynomial, you have to know these properties so that you can, calculate such coefficients for NPDE. So what we will do is, in order to extract AN, what do we have to do? What should I do if I have to exploit the normalization or optimization property? What would I do? My variable is rho, K and rho. Here it's alpha x. So that has become rho in some sense, right? I mean, so if I have to extract, what do I have to do? Unfortunately, it's not even 1, right? I mean, that's under thing, then it is. What's the trick normally? I mean, I just want you to tell me the trick that you use to get your summation, all that, and then. I mean, I can combine both of them into what? If it's orthonormalization property, I will put a square over 2, j square mu plus 1, delta alpha beta, right? I mean, that's what I would have written this in one expression like that, right? I mean, I wanted to split this, but so you understood what I was trying to do. Delta alpha product of that. If I wanted to combine both of them, then it's called orthonormal property in one expression. Both of them are combined into one, right? All right. So
we lose the alpha in the second term.
which one? Here?
Yes.
Yes. Yeah. It's exactly the same argument. Yeah. So what should I do with that?
Multiply by Jm.
Jm or J0, but the different one.
Well, yeah, it would.
Because
It-
that's
it
why
is
it is,
Jm.
use this, the same,
Oh, you're right.
yeah, the subscript is the same, okay? Argument is different. Kn, let's call it, okay? Rho, rho do, not just rho, so that's a normalization property with the weight factors there. What one says the weight, when we did the eigenfunction, we had the weight factor. In this case, it's a weight factor, is equal to summation, n equal to 1, a sub n, 0 to a, j0, kn rho, j0, kn rho, rho d rho. Okay. So we are multiplying by this and integrating between 0 and a. So this one is what? This quantity is, based on all that, what is that? That's combining both of them, right? That expression, right? So that is delta n a squared over 2. Can I call it j square 1 because it increases by 1, right? Kn rho delta n, right? So the summation, because the canonical delta function, the summation will disappear. And I can write that as what? A sub m, j1 square, right? Yeah. This is square, I just want to make sure, yeah. So the right hand side is what? Now, if you apply the orthonormalization property, what is that? Can I write n equal to m, right? Sorry, this should be, after evaluate, this should be alpha a, because I think we have already evaluated that, right? It should be independent of x, right after. Yeah. Because this is between 0 and a, alpha a. Okay. All right. So so this is j1 squared kna. What else should I write?
A sub n.
A sub m, right? Because n summation is over n is equal to m, right? So what was, this was N or M, okay. So all of them are N, okay? Because you have to choose a particular N. This N becomes M, and then A sub M, the coefficient.
So if A sub, okay, so if
Yeah.
A sub M, or if M equals to N, why are we spending so much effort to make sure that we have the correct one there?
Which one?
It seemed like there was like a major question of whether or not we should have A sub N or A sub M, but if we've defined that they are,
No, because this is summation is over N. So of all the N's, I'm choosing this one by which I have multiplied.
okay.
If it's K2 row, let's say, okay, I mean, so we are choosing whatever you multiply with the specific, whatever you multiply by, okay, so M is specific, N is not specific, right? Yeah. So this was equal to, unfortunately, we still have not, is equal to what? That part is wanted, then this is equal to 0 to T of T naught, 0 to A, T naught, J0, Km rho D. Okay? All right, I'm still not done, right? I mean, it looks like I still have to do a lot of things. That's what happens with once you get into complicated. So A sub M, I have an expression equal to 2 T's, the temperature at the bottom of the cylinder, divided by A squared, okay? And I have 1 over J1 squared Kma. These are all specific things. And I still have this another integral to evaluate, and unfortunately, I have one more step to go. Km rho d rho. Okay, this is expression for that. Now,
We're integrating over the radius.
what did you say?
Are we integrating over the radius?
Yeah, that is 0
So
to
0
A.
to A,
Yeah,
okay.
0 to A. Yeah, sorry. Yeah. So yeah, that is integrating over the radius. All right. Now, what is this? I mean, I know how an should look like, but now I still have to get this. And I'm going to use one more property which we had done actually in the class. All right. Remember when we had the generating function of Green's function, we had some recursion relationship, and there was another relationship that we had derived in the class. And it's like this. We went back to the definition of the Bessel function in terms of summation, multiplied, and then we had proved this relationship. It's nothing but z nu, j nu, it sort of goes down by 1. Okay. All right, this is an expression we got from the Bessel function, generating functions, and use the property of j nu. Now I need what? If I put z equal to km rho, let us say, and then nu equal to 1, then I'll get a, yeah, okay, let's put nu equal to 1 in this also, okay? So if I put nu equal to 1 and z equal to km rho, then I have this expression, km rho, because z is 1, that's good. And then I have, what is it, j1 km rho. Alright, this is nothing but equal to rho times j0 km rho. Right? So z was km rho, nu was 1. This is what I'm doing. This is substitution I'm doing. And nu equal to 1, so this is jz km Alright? Now from here, what am I? I'm after this. I need to get this guy. Km is the constant, rho is, so if I now integrate this expression between 0 and a, okay, with respect to rho, okay, what is my left hand side? I can cancel km because that's a constant, so I can cancel that. So what is this expression? D over d rho of rho times j1 km rho. What is that? I have to integrate that. What is this expression? 0 to a. All right. So what is this?
Just evaluating the thing at
At
A.
A. At A, yeah, exactly. At rho equal to 0, that will be 0. Okay, so this is simply this term, right? I mean, you integrate that. So this is nothing but A times J1 Km A, right? At the denominator, because of that, is 0. And Km is a constant. So I can pull that out. Okay. All right. So my left hand side is then. So I have this integral, right, which is 1 over km of all this. So I do have this integral now in place. I evaluated that. Is simply a times t0 divided by k sub m times the first order Bessel function j1 km a. And so I can calculate a sub m. A sub m is nothing but, I can calculate one, cancel one of them also. I have a t0 km, so 2 over a square, right? 1 over j1 km a. This becomes, I think I can cancel that, so it's 2 over a. So this is the solution we are seeking, right? So I can now substitute a sub n, so put m equal to n here then. N going from 1 to infinity of 2, that can be pulled out because they are constants. 2t0 over a, 1 over kn, j0 kn rho divided by j1. M can become n now because it's an I need, right? Exponential of minus kn z. So put, in order to get it, just put change m to n. Yeah, this summation because that's not a it will depend on n. So you can see how, although we got the general solution, this coefficient it depends on the geometry, a little bit of all these, the radius of your cylinder, whatever it is, and all that functions. It is not easy. It's not trivial. It is pretty complicated. And to get analytical solution in a complicated geometry with boundary condition, once you go away from Cartesian coordinate, it is messy because to solve a PD problem exactly, you have to learn you have to learn first, second order differential equation and all the properties of all these special functions, not just also non-normalized other things. So that's why people go to in the real complicated realistic problem, people solve it numerically, and rather than analytically, because it's not at all trivial. I just want to show you this because it is not. You can appreciate the difficulty of all these things, right?
But this kind of question wouldn't show up on a test or anything.
Of course, I'm going to give you that. So I can give you F, all of you guys.
There will be a tie-shaped hole in that window.
And I have to do it in the classical style. Just to, you know everything, yet it is difficult. That's all I want you to know, right? Most of the things you had, the PDE we had done. General solution form, no problem, I know it's going to be Bessel function, something exponent decay. Up to that, it was easy. To get this last one thing, the Fourier coefficient of this, it's not trivial. You have to learn a lot of things, and that was the reason we were doing the generating function method, because you can get the properties, right? It's it is not a very difficult geometry. The boundary conditions were fairly simple, but yet it is not. So I just want you to, it is a very simple problem otherwise, but it is not easy. Okay, I just have some time, so I'm just going to maybe get started with Fourier series. It's light is not like this. Because it's important for you to solve them. I'm going to give you a homework problem today, solving PDE, and you may want to learn a little bit better the Fourier series so that you can solve at least in Cartesian coordinates the problems. All right. I just want to introduce in a different way. Let me, you can write, can I write a function like this, f of x? I've done nothing, right? Half of x, it is gone, right? The second term is gone, so I can always write. But if f of x is even, right? That's a property of even and odd function, right? So what happens if I put if f of x is even to that expression? The second term drops, right? If f of x is even, this is what I can write it like this. Okay. If f of x is odd, f of x is half f of x negative right? That term is if a function is odd. This function if f of x is odd, even. So it looks like any function can be written as a part which is even and an odd function. You can cook up like this, right? Any function can be split into an even function and an odd function, right? That's what this is a very trivial statement I wrote, but it also, because we also know a property of an even function is if f of x is even, f of negative x should be this. If f of x is odd, f of negative x should be negative of f of x, right? So based on that, we know that if f of x is even, we have only that term. If f of x is odd, we have only that term. So any function can be written as a combination of odd and even function. So I'm just saying Fourier series, what do we do? Combination of sine and cosine. Sine is an odd function, cosine is an even function. So I'm just motivating you why we write it in terms of that. So the Fourier series, of course, there are various conditions, but we write a function f of x as the following. Let me write the cosine first. It doesn't matter, but I'm just, because I put that there, so. Okay, so function f of x is a even series, a combination of odd, even and odd function. Okay, so that's sort of you can rationalize why we are doing it that way. But this is called Fourier series generally, and these are called as Fourier coefficients. So in general, you can write such a series if a function is normally, there's something called Dirichlet condition that has to be satisfied to write a function in terms of a Fourier series. And what Dirichlet said was that if the function is periodic, yes, you can write it. If a function is completely continuous everywhere, you can write Taylor series, right? I mean, now Fourier series also is applicable if a function has, it's not, it can finite jumps it could have, and the derivative can be, not, it's not well defined at these jumps. Yet you can write a Fourier series. But the number of such jumps in a function in a given domain, there cannot be infinitely many. If there are only finite number of such jumps, you can write it. Okay. So even if a function is, even if a function, if f of x has discontinuities, but only finite number of such, finite number of discontinuities, there's another condition that integrated over one period, this quantity has to be finite. Okay, this is an important condition because if this is not satisfied, Fourier series is not possible. That's why you go to other transforms, other representation of the function, like Fourier transform, Laplace transform, and all. Okay, so this is an important condition also. The integral of the function over a period must be finite. In this case, L, okay.
Why are we taking the absolute value of it?
I think it's f of x squared also is there. I think this is a condition for Dirichlet gave this. We'll see why this is important when you go to Fourier transform. Okay, there are lots of functions. Let's say exponential of x or something like. I mean, there's function like even x over infinite domain. Of course, it's not going to happen. It's going to blow up. I mean, there are functions which will not satisfy this condition. So it has to. It's almost like some convergent criteria, I think. I mean, so let me just say maybe this way. Maybe it's easier to understand. Okay. Although I said if a function is periodic, okay. Even if a function is not periodic, you still can give a Fourier series representation. Okay. The way we do it, this is where those things are all coming. Okay. I mean, supposing I have a triangular wave, something like this, okay. And can I give a Fourier series representation? No, of this function. It is not periodic, right? So what you can do is you can sort of make it periodic, okay? You just artificially extend this figure somewhere like this, or maybe you can, make it even function if you wanted. You could have made it like that also, okay? But although you made it, some domain here. Okay. So these are some appendages you have to the function, the original function that they're given. So you write this period using the Fourier series. You will write some representation for the function between 0 and L. Okay. That Fourier series representation is not possible. It's not valid for the entire domain. It's only valid for a very restricted domain. Okay. It is. Whereas if it's truly periodic, it can be represented. Fourier series representation is valid for all x's. Okay. But if it is something, you take any function. This is what I'm trying. Can I represent any function by Fourier series, right? That's a question. I think, so what Dirichlet says is not all of them. It must also satisfy, I think this fx squared is perhaps is there. I think I need to check on this. It has to be bounded, basically. This function, so there may be some function which may not be bounded in the. So that is, I think, one of the restrictions which Dirichlet has given on top of all others. So you cannot blindly say every function, although when I wrote f of x equal to, it looked like any function could be written as a part of sine and cosine, right? When I wrote f of x equal to. That's only to rationalize why I put sine and cosine. But Dirichlet came and said, no, not any function can be, written automatically into Fourier series. There are some conditions, and he has imposed some condition. One of the condition happens to be this one also. Okay, the function has to be bounded basically, okay, in the domain that you are trying to, it's not, it'll never be valid for 0 to infinity, okay, may not. So I'm just, at least within one period it is finite. Is it true for an infinite domain? Probably not. Like f of x is one example. It's not going to be bounded, right? I mean, x equal to infinity. Can I write x as a Fourier series? Just simple x. Probably not. Okay. So you need to come up with other representation for a simple function like f of x equal to x.
Yeah, because then you could just make your own function which is equal to x over some amount of it, but then it's also periodic, and then you have a Fourier representation of x.
Probably, yeah. We can, yeah. But then it is not that representation you have given is not true for infinite domain. It will again be true for a small portion of the domain only. It is you have a Fourier series representation between maybe a small domain, which is maybe whatever the fake periodicity that you created, not from 0 to infinity. Okay. So that is an extra condition that we have, and there are other things, but I think this may be one of the most. Yeah, there's also says one of them. It says if a function is a bit oscillating, it can have only finite maxima and minima in a given period. Okay, I mean that may also be connected to some convergence, but these are sort of a few conditions that we have to check before we decide if a function is, if a function can be represented by this or not. Maybe we are already time. So we'll start from here. I just want to give you, but we want to calculate these coefficients, which is what, I wrote the expression last time, but I just want to prove that to you, and we'll just move from here because, different representation of function we'll talk about. Fourier transform, Laplace transform. It's also representation of function. There are, for instance, this is over finite period, right? Fourier transform is something over infinite domain you want to give a representation. That has to be, although it's infinite domain, it's still, this quantity is finite. So you go from Fourier series, you want to give a representation where it's true in an infinite domain. If there's Fourier series, normally we're using a finite domain like the periodicity over a certain length, right? So from there, I will go to another one, which is Laplace transform. Why do we have all these different representations? Because it is a way to represent a function in different ways. There may be functions that do not even satisfy that, right? So I'll force them to satisfy that by putting maybe some exponentially decaying function or whatever it is. And that's what will give you the definition of Laplace transform. Where does the definition of Laplace transform come from? So we'll talk about different ways of representing function. This is for generally for periodic function, but you can remove that condition also, the periodicity condition. But then whatever representation you have with the sine and cosine is valid for certain domain only. For even in this case, like we will normally talk about all these jumps, right? Let's say it is 0 and 1, right? Whatever representation you give, okay, you have Fourier series representation here, but you do not have it in the region of the jump, right? In the region of the jump, the function will be just the average of whatever value you have here and here. So this kind of a series representation, for the Fourier series representation, can be, given whatever you give, that should converge to value 0. Here it will converge to combination of an and bn should converge to 1. Okay, that's what the Fourier series representation means. Whereas here at the junction, the value will be something like 0.5. Okay, whatever the series representation you give, here it should become average of whatever values you have there and here. Okay, so these are certain things that we can talk next time about it. All right.
How many sides is this?
Yeah, the PDE will be covered, yeah. We have a, hypergeometry, control hypergeometry,
You know the Polar Express
what
was
do
really
we
big nerd.
Green's function method, derivative
Oh,
method.
yeah, know it all?
Yeah, know it all.
Hmm?
I have a thing called Polar Express answers, which I.
Not series, I mean, only the derivative method, yeah, you have to of course remember this.
Technically, you are correct, that it has an infinite number of
What
sections.
did we do there? Term level
That will never change.
and
Technically
information.
correct.
Yeah, mainly homogeneous definition, term level. Right, yeah, partial differential. At least you must know partition formats.
God bless context.
Yeah, okay.
Elated by most of their role that
I didn't know that.
yeah, he did the.
Dick it.
He did the.
Dick, tomorrow what?
Yeah.
Yeah,
What time did you have PLC?
Yeah.
Oh, no, do you have?
no, I've got a, no, I don't have anything, I can show. Where else? BAB?
So I take care.
Yeah, so I can give you the information, I already reserved the room.
Cool, yeah, it's at one Discord.
Actually.